Hi, my name is Michael Tanzer, and I'm here to present the paper Memorization versus Generalization in Pre-trained Language Model by myself, Dr. Sebastian Ruder, and Dr. Marek Rai. In the past years, we have seen a rise in the use of large-scale pre-trained language models. These models contain billions or trillions of parameters and are trained on large amounts of general-purpose data. Because of this, they're able to learn quickly from relatively few examples and are able to generalize well to out-of-distribution examples. Previous work in this area studied in great detail what these models learn and how this knowledge is then used in downstream tasks. What still remains partially unclear is how these models learn, which we believe to be fundamental in order to know in which scenarios these models fail and how we can improve them. Therefore, our goal is to qualitatively study in depth how complex pre-trained models learn by analyzing their generalization and memorization capabilities. Throughout our experiments, we focus on the named entity recognition token classification task. Specifically, we use the Conor 3, JNLPBA, and WNUT17 datasets. In terms of studied models, we focus on BERT, as it is the most common and most studied model, but we also validate our claims on other models, such as dBERT and ProBERTA. In this presentation, we only report results on BERT for brevity, but all models share the same pattern for all our experiments. First, we analyze the training dynamics in noisy settings. To do so in a controlled manner, we train BERT on the Conor 3 datasets in the specific example we have here, where some percentage of the labels were replaced with a wrong label. In our experiments, we use 6 different datasets with noise from 0% to 50% in steps of 10%. In all our plots, darker color corresponds to higher noise that we add to the dataset. On the left here, we can see the training and validation performance during BERT fine-tuning. From this plot, we can see how the training can be divided into 3 very distinct phases. The fitting phase, where the model learns to generalize and where it learns simple patterns that explain a large portion of the data. Here, both training and validation performance rise very quickly. Then we can see the settling phase, where nothing really happens, everything seems to be stationary, and the duration of this phase seems to be inversely related to the noise added to the dataset. The second phase is much more prolonged in BERT compared to other large pre-trained models developed for other modalities, for example, imaging models. These other models immediately start to learn the noise and don't have this flat phase. Finally, we also notice how the top validation performance is very close between all models despite the higher level of noise, suggesting a strong robustness to label noise of pre-trained language models. Finally, we have the memorization phase, where BERT rapidly learns the noise present in the dataset, increasing the performance on the training set but degrading the performance on the validation set. The observations we just made are also confirmed by this plot, where you can see the training performance on the of the noisy examples only. Here we can see how the model starts as a random classifier for the noisy points, and then quickly learns how to ignore them by intentionally misclassifying them. In the third phase of the training, BERT starts to memorize them, which is shown very clear by this step-like pattern that we can observe. This shows that the model cannot find any pattern that describes all the noise, and is simply forced to memorize the points epoch after epoch. We also use some tools introduced by Toneva et al. To study the learning dynamics of the model. In particular, we use the following concepts, which are learned examples, which is every example that was classified correctly at least once during the training. Forgettable example, which identifies those points that were learned and then forgotten at least once during the training. And finally, we call unforgettable those examples that were learned and never forgotten until the end of the training. Using these tools, we can study how BERT learns and forgets information during its training compared to, for example, a BiSTM models or a non-pre-trained BERT. Here we show that how BERT forgets much less compared to the BiSTM model, and we can also see how the pre-training process plays a considerable role in retaining information during the training. A non-pre-trained model has a very similar learned example ratio, but a far higher forgettable examples ratio. Using these new tools we just introduced, we can also go back to the 3 phases of the learning and see how studying learning events confirms that what we had mentioned earlier. Here we can see a plot of the ratio of learned events on the training set during BERT fine-tuning. We can see how in the fitting phase, BERT learns most of the examples, and then in the settling phase, it simply stops learning any new examples. As we can see in epoch 3 and 4, there are 0 examples learned. And finally, in the memorization phase, it starts memorizing the noise. The memorization here is clear by the fact that the more noise we add, the higher the lines are in the third phase. So darker colors, it corresponds to more noise in this case. Finally, we also look at how BERT works in low resource scenarios. To do so, we construct a controlled setting where we take a common dataset, CONOLO3, and remove all but X sentences containing a given label. The goal here is to study how the training and validation performance change as X changes. Here we show the classification performance for the training and validation datasets on 6 different versions of CONOLO3, where we left a varying number of sentences containing the log class. Here, darker color represents fewer sentences, and lighter colors more sentences available. In particular, here we have datasets from 5 to 105 sentences with the log class in steps of 20. We only report the F1 score on the log class in this specific plot. We can see here that for fewer available sentences, the model's ability to generalize is greatly reduced, and when only 5 sentences are available, log tokens are treated as noise and learned during the memorization phase. Studying learning events, we can also see how in this low resource scenario, the data is not learned in the fitting phase as one would expect, and as was happening before, but it is instead mostly learned during the memorization phase, as if it was noise for the model. This essentially means that the model couldn't find a simple pattern to describe the log class data when only fewer sentences were available. To address BERT's poor performance on the few-shot learning datasets, we proposed a new model, Proto-BERT. It is a combination of BERT with all its pre-trained knowledge, combined with the few-shot learning capabilities of prototypical networks. The idea of a prototypical network is that it produces a mapping to a space where the examples of each class are clustered on a per-class basis. The classification is then performed by finding the class centroid closest to each test example in this new embedding space we have produced. We then propose to augment BERT with a prototypical layer devised specifically for token classification. We also make several changes to the standard implementation of a prototypical network in order to speed up the training process without any loss of performance. If you compare the performance of Proto-BERT with the one of a standard BERT model, we can see how Proto-BERT vastly outperforms BERT when fewer sentences are available. As the number of sentences increases, the two are roughly equivalent, and in some cases, Proto-BERT even outperforms BERT in non-low resource scenarios. Thank you very much for listening.